Hello everyone, my name is Anuj and I am here to present our work on dynamically distributed intelligent transport system, also known as D2ITS. So at high level, one of the components of D2ITS is vehicular communication. And the job of vehicular communication is to send the information for self-driving, coordination of flow traffic, communicate the road conditions, collision avoidance, and so on. So these are the basic kind of functionalities a vehicular communication should do. Vehicular communications are divided into two types. One is vehicle to vehicle, other is vehicle to infrastructure. By infrastructure, we mean roadside units like a Wi-Fi access point or a base station like LTE. The challenges of ITS, which has a unique challenges, are low latency because the messages are in order of tens of milliseconds of latency, reliability, scalability, and geographic decentralization. What that means is like there is a high possibility that you cannot guarantee that vehicle is always connected to a wide area network. So there might be some zones where even though network is good, but the vehicle cannot communicate because it is overshadowed by buildings around it. So we need to have some kind of architecture which doesn't let this happen. So with that in mind, we came up with a new architecture. It was a new architecture, something like shown here, where we have a main controller, which is a controller maintained at the top level by the ISPs. This could be co-located with like an LTE base stations, which are constantly maintained by the network vendors. This main controller has a view of the whole network, but it delegates the control downwards. Next level is a secondary controller. Secondary controller communicates with the main controller through vertical east-west interface. We have borrowed the name from SDN terminology. Secondary controllers talk to each other through horizontal east-west interface where they share both control plane message as well as data plane message. In terms of control plane message, these are the messages which could be like sharing what is the status of the controller, what cars they are controlling, if there are any other level of information like what kind of tertiary controllers they are controlling. That is the control plane message. Then the data plane message is an information which you want to share across. For example, if a vehicle wants to send message to other vehicle which is not in the same area, so the message might hop between secondary controllers until it reaches to the vehicle. Then we have another layer, other hierarchy that is called tertiary controllers. Tertiary controllers have a unique functionality where they can have both and switch. They can act as switch as well as controllers. If they are acting as controllers, then it is their responsibility to control the nodes below them. But if they are not, they just act as simple nodes. The secondary controllers are like can use short range communication or mid-range communication like Wi-Fi access points. The tertiary controllers between the nodes can use something like IEEE 802.11p, which is short range communication. So this is a high level architecture, and I just want to reiterate that the depth of the controllers is arbitrary and it depends on the application. For example, in the next slide, we have ITS. So we have 3 depths of controllers. But if you have any other application, we can scale accordingly and increase the depth depending upon the application. So in this case, we have a roadside base station, which can be thought again as an LTE base station. There's a controller co-located with it. Then we have roadside units. Again, as I mentioned in the previous slide, they are like Wi-Fi access points, and controllers are co-located with Wi-Fi access points. Then we have a third level where vehicles are acting as controllers and they are controlling the vehicles below them. And the blue circle I have shown here, we are calling it as domain, but it essentially is the range of what the vehicle as a controller can cover. Vehicles can communicate with each other, the control plane message as well as data plane message. So just to reiterate that the functionality which we are trying to hide here is that secondary controllers or even the main controllers or tertiary controllers can instantiate themselves accordingly. For example, if secondary controller is saying that it is getting overloaded, it can select a tertiary controller from a group of vehicles and tell it, okay, now you are the tertiary controller, you take control of XYZ cars. So from there onwards, the tertiary controller will take care of those cars, and only if required will communicate with secondary controller for the next level of hierarchy. So that is what we mean by control delegation here. So what is D2ITS? D2ITS is a dynamically adjustable and distributed control plane. It has lower latency and lower overhead. It's a scalable architecture, and it can delegate the control, as I mentioned in the previous slide. And to add on top of it, the whole architecture is designed in such a way that it is network agnostic. So this was a high level overview of our architecture. Now we wanted to showcase a use case. So in this case, we took use case as road hazard warning application, also known as RHW. This is an application which HC came up back few years back. They divided messages into two categories, what is called known as DEMS, Decentralized Environmental Notification Messages. These are the data plane messages from RHW perspective. They are subdivided into two categories. One is emergency, other is warning. Emergency messages are low latency messages and have a shorter area to be covered. So for example, if you have an accident, you just want certain vehicles like within certain radius to stop. You don't want that big radius for cars to stop. So that is what emergency messages are. Warning messages are more like roadside congestion, traffic information. Then they also categorized control plane messages, also known as CAMs. CAMs are mostly about the location update from the vehicle, speed at which vehicles are going through, and if new vehicle is coming in, the new vehicle is joining into this network, they need to send authentication and security messages. Those all happen under one umbrella of CAMs. So based on what HC defined, we decided that it makes sense for D2ITS to handle these two messages separately. So for CAMs, what our controller does is when controller receives a message, CAM message from a vehicle, it updates its local database information about the vehicle and also sends this information to the neighboring controllers so that they also know what is going around with the neighboring controllers and what vehicles are they controlling. So that's all what we do with CAM messages. For DEMS, once the controller receives a DEMS message, it checks a type. If it's an emergency message, then it just broadcasts to its own domain, the range to which the vehicles are connected. What would this mean is that we are making sure that the latency is reduced and we are not flooding the whole network, but just the domain of that controller itself. But if it is a warning message, what we do is, what the controller does is it computes the relevance of that message, if it is impacting the neighboring controllers or not. If it is, then the message is forwarded to the neighboring controllers. Otherwise, it is just sent to the controllers, to the vehicles of the controller which are getting affected. So the next part of our design was to showcase the control delegation. So we took handover as an example, but handover is an overloaded term, and I just want to distinguish between the kind of handover we are talking about and what already exists in the networks like LTE, 3G. So I categorize what is happening in 3G and LTE as physical control delegation, where the link between the two entities is broken and a new link is established. I'm not talking in this work, we focus more on logical control. The logical control meaning how the vehicles move, how the controllers move their control from one of the vehicles from one controller to another controller, be it vertically, meaning secondary to tertiary, or horizontally from secondary to secondary or tertiary to tertiary. So we decided the two kind of criteria for initially is for doing logical control delegation was the proximity based, that is RSI based, or load based. So at a high level concept, The logical handover process can be categorized into three steps. One is the discovery. What are the candidates available to which we can hand over? Then, based on the information the controller has, it can select the best available controller. And then third step is to actually do the association. This is where the physical handover comes into place, where the link between the two entities is broken and new link is established. So we also have categorized logical handovers into two types. One is controller initiated, where controller decides handover should happen or not. Other one is vehicle initiated, where vehicle by default would initiate and not worry about controller's decision. Due to the time limitations, I'm just going to cover the control initiated handover workflow. The controllers periodically send beacon messages to the vehicles. Once the vehicle receives the beacon message, they calculate the RSSI and the package lost for the respective controllers. Then they update the controller with the information saying that this is the RSI I'm getting from you and from the neighboring controllers and other kind of metrics. Based on the information received by the vehicle, the controlling controller decides, has the criteria for handover been met for this vehicle or not? So for example, if it is RSI based, they will check the RSI value which is being sent by the vehicle. If it is load based, they can check what is the current load which the controller has, and is it okay if they could hand over a vehicle to some other controller. If the criteria is met, then the controller sends this information to the vehicle saying that I am giving you the target controller where you need to initiate the request for handover, and just go and initiate the handover. So vehicle goes and initiates the handover. The prototyping which we did is like, we have three types of entities. One is the controller, which is just a plain RU STN controller. Then we have the tertiary controllers, which are like which can have both switch, which is the OVS, and the controller, again the RU controller. We have plain vehicles which are acting just as OVS. Then all these applications are running on top of MiniNet Wi-Fi. MiniNet Wi-Fi supports all different kinds of protocols. I would like to emphasize here that we added PubSub module into MiniNet Wi-Fi so that we can support east-west communication across controllers. So for the scenarios, we decided, okay, we need to have some kind of benchmark to benchmark our D2ITS application with. So we decided that we will have one scenario where we will have one entity, that is the one controller, co-located with an LTE base station, and there will be one vehicle which sends periodically the emergency and the information messages across to the vehicles in this domain of this eNode B. As you can see, it has a constant latency. There's no distinguish between the warning or the emergency message, and the latency is flat at 142 milliseconds. The reason for that is because for LTE, no matter where the location of the two vehicles is, even if they are adjacent, it still will go to the backhaul and come back to the vehicle. So there is no concept of an edge in this case. Then we ran this kind of a similar experiment where we have a vehicle which sends periodically the information and the warning messages and moves across two different RSUs. In this case, we have vehicle 4, which is sending these messages, and we are taking the results or the report of latencies from the vehicle 6. So as you can see, when the vehicle 4 was in the domain of vehicle A, it saw a higher latency because the message for the information message, because the message had to travel through the data plane traffic of the RSU A and the controller A, and then go to controller B, and then from controller B go to vehicle 6. But as the vehicle 4 kept moving closer and closer to domain B, the latency started reducing because now there is no hopping of the message from one controller to another controller. So the information message latency reduced at around 148 to 150 seconds into the experiment. As with the emergency message, you can see even though the vehicle was sending the emergency messages in the domain A, vehicle 6 never received the emergency message because emergency messages are only specific to a domain. Hence, for the first half of 150 seconds into experiment, there was no emergency message. But as the vehicle went into domain B, there is an emergency message. Then I'm showing another case of RSSI based handover. In this case, we decided we will have only one vehicle, and this vehicle will go across through different RSUs, and it will send a ping message, a ping from the vehicle to an internet, maybe say Google DNS 8.8.8.8. So as you can see the results, the main thing we want to highlight here is that even though you see the vehicle is going across, there is never a link breakage, and the latencies are almost all consistent around 20 to 22 milliseconds. You might see there are peaks around in between in this graph. The reason for that is because the way we have set up our experiments, there are cases where the vehicle is on the edge of one of the controller's domain, but there is no other controller where we could do the handover, hence these spikes. And as the vehicle moves closer and gets into the overlap zone where both controllers reads are overlapping, the system is intelligent enough to do the handover and reduce the latency. So I have more experiments in this slide later on, but because of time, I'm just not going through them. Feel free to look at the slides, and there are results for the load-based vehicle-to-vehicle communication and smart rerouting-based example we did. To conclude, here we have demonstrated that we have a hierarchical and reconfigurable framework. It supports both low latency and increases the programmability, has lower overhead, and we hope that with this, the messages we have created in this framework can be added to ITS RHW framework. Thank you. That's the end of the slides, and I'm happy to answer any questions in the Slack channel. Thank you.